Hi there. In this lecture, we're going to see the topic of distributed graph processing, which has come into prevalence in just the last few years in industry. So we'll see what distributed graph processing is, and we'll see a little bit of the overview of Google's Pregel system for distributed graph processing. Pregel is not an open source system, but Google has published a paper on it, and based on that paper, several systems have been built, including Pregel-like systems, as well as much more advanced systems that are faster than Pregel. We won't get to discuss all these systems in detail, but hopefully this lecture will give you enough of an inroads into the topic that you can go and look up these systems if you're so interested. So what is a graph first? A graph is not a plot. We are not talking of a graph as in a curve or a series of dots. A graph instead is a network. And a graph, like a network, has vertices or nodes. For instance, Facebook, the social network, can be represented as a graph, where each user is a vertex or a node. A graph also has edges. An edge connects a pair of vertices. For instance, in the Facebook graph, an edge would be a friend relationship between, say, you and one of your friends. That would be one edge. The friend relationship between you and a second friend would be a different, separate edge. Okay, so a graph consists of vertices and it consists of edges that join pairs of vertices. So there are lots of graphs around us. So on the right, I have an example, a picture of a graph taken from Wikimedia. Here you'll see the vertices or nodes shown in red and the edges shown in black, okay, joining pairs of nodes. So there are graphs all around us. The internet itself is a graph where the vertices are routers or switches, and the edges are actual links joining these routers or switches, links that actually carry packets and traffic. The World Wide Web can be represented as a graph where the vertices are web pages and the edges are URL links where one page points to another. So if you have a URL on one page pointing to another, that's an edge in the World Wide Web graph. Now, the World Wide Web graph is a special kind of graph known as a directed graph because edges are directed. Page A might point to a page B. That does not mean page B also points back to A. So edges actually have directions. They are unidirectional, and so the World Wide Web graph is an example of a directed graph. Graphs where edges are bidirectional by default are known as undirected graphs. Social graphs such as Facebook are again an example of undirected graphs. Twitter is an example of a directed graph because you can follow someone, but that doesn't mean they'll follow you back. LinkedIn is an undirected graph as well because the edges are bidirectional. Other graphs include the DNA interaction graphs, ecosystem graphs, chemical reaction graphs, and a whole lot other graphs. So in fact, in any area of science, you can find graphs, you can draw graphs, and then you want to make sense of these graphs. So graph processing operations try to derive properties from these graphs. They try to summarize graphs into statistics so that you can understand what the graphs are telling you much better. For instance, you may want to find shortest paths between pairs of vertices. In the internet graph, this is useful for shortest path routing so that your packets can get routed fairly quickly. In LinkedIn, shortest paths is useful to find the degrees of separation between you and someone else. So if you've used LinkedIn, you might notice that it says this is a first connection or a second connection or a third connection. That's the degrees of separation, and that's obtained by running the shortest path algorithm to see what is the distance between you and another user, what is the shortest distance between you and another user. In dating websites such as Match.com, graph processing operations are used to find good matches between pairs of users. And there are many other examples of graph processing applications being used. So what's so challenging about this? Well, one of the biggest challenges is that these graphs are very large. The human social network has hundreds of millions of vertices and billions of edges. If you consider the graph consisting of all the humans in the world, where every vertex represents a human in the world, and edges represent friends or relative relationships, then that graph has 6 to 7 billion vertices and many hundreds of billions of edges. The World Wide Web itself has millions of vertices and edges. So these are very large graphs. They're so large that the entire graph cannot be stored on a single server for processing. Even if it were to be stored on a single server, it would be really slow on that server, even if the server had many processors. So this is where the distributed cluster or the cloud comes into action, where you can use a large number of machines in a cloud infrastructure or in a data center to process a very large graph very quickly and very efficiently. So what does a typical graph processing application look like? Here we are knocking off a typical graph processing application. We are not yet talking of the distributed version of it. I'll talk about the distributed version of it soon. So a graph processing application works in iterations. So one iteration leads to the next. Each vertex is assigned a value. At the beginning of the iterations, the value is some default value like 0. Then in each iteration, each vertex in the graph gathers the values from its immediate neighbors, vertices who are adjacent to it via an edge. So for instance, at the vertex A here shown in the figure, its immediate neighboring vertices would be B, C, D, and E. Those are the vertices that join it directly with an edge. So A would obtain their values at the beginning of the iteration. So B would send its value to A, C would send its value to A, D would send its value to A, and E would also send its value to A. Once it has all these values, A would then use its immediate neighbor values along with its own value to compute its own new value. And then at the end of the iteration, it would send out its new value to its immediate neighbor. So it would send out its value to B, C, D, and E. Then B, C, D, and E, in this iteration, they had also used the value of A to compute their own new values. And in the next iteration, again, they'll use a new value of A to compute their own new values. So this series of steps 1, 2, 3 is done for every vertex in the graph during each iteration. So you keep doing this iteratively, and how many iterations do you have? Well, you can either have a fixed number of iterations after which the graph processing terminates, or if the kind of application you're running actually converges, for instance, the shortest path algorithm is one of those algorithms that actually converges, then after a while vertices will stop changing values. So they'll get values, but their new value that they compute in the second step will be the same as their old value. And if all the vertices in a given iteration do not change values, then the computation has terminated. So in order to run this in a distributed system, can we use Hadoop? That is the first thought that we have. Well, if we wrote this using Hadoop, essentially we would have a multi-stage Hadoop where you would have one map and reduce phase for each iteration. So each map and reduce stage would be one graph iteration. So if you had 100 iterations, you would have 100 chained Hadoop or map reduce jobs after another. You would use the vertex IDs as the keys in the reduce phase so that the information about a particular vertex would get routed to the same reduce task, which would then use it to compute the new value for that vertex. This is attractive because, of course, Hadoop is well known, so it may be fairly straightforward to write this application up in Hadoop, but it's fairly inefficient. At the end of every stage, that is at the end of every iteration, you essentially are transferring all the vertices values over the network to the reduce tasks, or almost all the vertices values. And this can be very, very slow because essentially you're transferring the entire graph during each iteration over the network. That's really, really slow. Also, if you're using Hadoop, at the end of the reduce phase, the vertex values may be written to the HDFS, the distributed file system, and that makes it even slower. So Hadoop may be easier to code up, but it's very, very slow as far as the graph processing is concerned. And our main reason for using distributed infrastructure, data center, was to speed up graph processing. So what comes to our rescue is what is known as the bulk synchronous parallel model, where essentially you have local computation being done at multiple processors parallelly. Here you think like a vertex, so each vertex is computed separately by a different processor, but at the end of the iteration, all the processors meet a barrier where all of them wait for the other processors to complete their iteration, and only then do they proceed to the next iteration. The BSP, or the bulk synchronous parallel model, was originally proposed by Valiant, and that is what is used by many of the distributed graph processing engines today. So in the basic distributed graph processing engines today, you think like a vertex. You assign each vertex to one server, so each server gets a subset of the vertices in the graph. Thereafter, in each iteration, each server performs the gather, apply, and scatter for each of its assigned vertices. For each of its vertices, it gathers all its neighboring vertices values. So for a given vertex that a server is assigned, it gets the values from the vertices that are immediately joined to that vertex by an edge. Some of these vertices may be local at that server. Other vertices may be located on other servers. So you fetch their vertex values over the network. Then once you have these values, you apply. In other words, you compute this vertex's new value using its old value and the values of its immediate neighboring vertices, and then you scatter. You send the new value over to these neighboring vertices. Okay, so this is again very similar to the 3 steps we had discussed earlier in the non-distributed version of graph processing. So here it makes a difference. What makes a difference here is which server you assign a given vertex to, because this can reduce the amount of communication. If the neighboring vertices of a given vertex are on the same server as itself, then essentially you can fetch their values without involving any network overhead. So there is a couple of options in assigning servers to vertices. The first is hash based, where you take the vertex ID, you hash it using a well-known hash function, and you then take modulo number of servers, and whatever value you get is the server number to which that vertex is assigned to. Okay, so again, this is random, but it's consistent, and this should be familiar to you because this is essentially just consistent hashing, as we've discussed in peer-to-peer systems when we discuss distributed hash tables like CARD. A second option is locality based, where you assign vertices with more neighbors to the same server as its neighbors. So a vertex that has a very high number of neighbors is located on the same server, is assigned to the same server as its neighbors, and so fetching those neighbor values are just local operations and do not involve any network overhead. This reduces server-to-server communication volume at each iteration. Now, the Pregel system by Google follows the bulk synchronous parallel approach, and here is in a nutshell how it works. Pregel uses the master worker model. There is one master server and there are multiple worker servers. These would also be master daemon, the master daemon and the worker daemons running at each of the other servers. The master server is responsible for maintaining the list of worker servers, monitoring them. If any of them fail, then you need to restart them and reassign any failed vertices to newer servers. And the master also maintains a graphical user interface and a web UI for monitoring the progress of the other workers. The workers in turn are responsible for actually carrying out the gather, apply, scatter on the vertices that are assigned to them, and also for communicating with the other workers in fetching the values of the neighboring vertices where necessary. Typically in Pregel, the persistent data is stored as files on a distributed storage system such as GFS in Pregel's Google or in the Bigtable system. And temporary data is also stored on local disk, and it's stored on local disk because essentially if the worker crashes and then recovers, you want to be able to start where you left off. So how does the Pregel execution proceed? Well, first of all, many copies of the program begin executing on the cluster. The worker daemon startup and the master daemon starts up. The master then assigns a portion of the input, that is a subset of the vertices, to each worker. Each worker loads the vertices from, say, the GFS or Bigtable and marks these vertices as active. And then in each iteration, the master instructs all the workers to perform the iterations. So the worker loops through its active vertices and computes a new value for each vertex based on its old value and the neighbor values. The messages that contain the new vertex values can be sent anytime during the iteration, but they need to be delivered before the iteration is done, that is, before the barrier is reached by all the vertices, by all the servers at the end of the iteration. When all the workers reach the barrier at the end of the iteration, then the master is informed about this, and it knows that all the workers have finished this particular iteration, and the master can then move on to the next iteration, and it repeats these three steps again for all the workers. When does the computation halt? Well, the computation halts when in some iteration it's true that none of the vertices are active and all the vertices are marked as being inactive, meaning their values have not changed since the last iteration, and when no messages are in transit during the particular iteration. This means that the computation has terminated, it has converged, there are going to be no more vertex value changes in the future. At this point of time, the master can instruct each worker to save its portion of the graph or its results, and you now have whatever values your application set out to compute, whether they are shortest path values, whether they are values about matching in a dating graph, or other values as far as your application is concerned. What about failures? How does Pregel handle failures? Well, Pregel uses checkpointing. Periodically, the master instructs the workers to save the state of their partitions to persistent storage. The state includes vertex values, edge values, and any messages that are in transit. And these checkpoints can then be used to recover in the future. Ping-based messages are used from the master to the worker for the master to keep track of the worker failures. If a worker fails, then the master reassigns the graph partitions to the currently available workers so that every vertex is still assigned to one server. And then the workers all reload their partition state from the most recent checkpoint, and then they start where they left off. So when you have a failure, essentially you might end up losing the value of the work since the last checkpoint. If you're checkpointing at the end of every iteration, then you lose at most one iteration's worth of work, and you can start from the latest iteration. So how fast is Pregel? For the single source shortest path, or SSSP benchmark, on a 1 billion vertex graph, which is a tree graph, with 50 workers, computing SSSP took 180 seconds. With 800 workers, it took about 20 seconds, which is pretty fast. When you increase the size of the graph to 50 billion vertices, which is a pretty large graph, the human social network graph in the world would contain about no more than 7 billion vertices. With 50 billion vertices and 800 workers, this takes about 700 seconds, which is about 12 minutes, which is pretty fast. So that wraps up our discussion of distributed graph processing. Graphs are all around us, and large graphs are all around us, whether they're internet graphs, World Wide Web graphs, or social network graphs. And we need to process these to make sense of them. MapReduce is an attractive approach, but it's not very fast. It's not very efficient. Instead, we want to use distributed graph processing systems such as Pregel by Google, or their offshoots, including open source systems like Piccolo and Giraffe, which are very much Pregel-like in their implementation, or other systems that are much faster than Pregel, including GraphLab, PowerGraph, LFGraph, and Extreme. These are systems that have come out of research projects in the last few years, and some of these are open source, and they're being used increasingly in order to process graphs in clusters.